the end of the lesson or session, students are expected to define X-ray emission spectrometry and its principles. Second, apply the techniques of X-ray emission spectrometry to analyze real-world examples. 3. Explore the various applications of X-ray emission spectrometry in different fields. Each element has electrons occupying specific energy levels, characterized by quantum numbers. A simple description refers to the lowest energy level as the K-shell, with subsequent levels designated as the L-shell, M-shell, and so forth. These energy levels are integral to understanding how electrons behave in various chemical environments. For elements with low atomic numbers, such as hydrogen and helium, the electrons in the outer shells are often involved in bonding interactions. These valence electrons dictate the chemical properties and reactivity of the elements, enabling them to form bonding with other atoms. However, for elements with high atomic numbers such as nickel and copper, the situation becomes more complex. The inner electrons, primarily those occupying the K-shell, are largely unaffected by changes in valency and bonding. This is due to their proximity to the nucleus and the strong nuclear forces acting on them, which means that they remain stable and do not participate directly in chemical bonding. Interaction with high-energy radiation. A simple example of how these inner electrons can be affected involves the interaction of a target atom with high-energy radiation, such as accelerated electrons or radioactive particles. This process can be visually represented in Figure 1. When a target atom is bombarded, an inner electron, typically from the K-shell, can be excited and ejected completely from the atom, creating a vacancy in the shell. You can see it in Figure 1a. The significance of this process lies in the resulting electron transition that occurs. After the ejection of the inner electron, an electron from a higher energy shell, in this case the L shell, can transition down to fill the vacancy left by the K-shell electron. As this transition occurs, energy is released in the form of primary X-rays. The wavelength of these emitted X-rays corresponds to the energy difference between the L and K shells, illustrating a fundamental principle of quantum mechanics. You can see it in Figure 1b. The research focuses on the behavior of electrons in various atomic shells and the resulting X-ray emissions when these electrons are excited and then relax. And the key findings in electron excitation and emission. Electrons excited from the L shell, which contains 2s and 2p orbitals with slightly different energy levels, lead to the emission of X-ray doublets known as the Ka1 and Ka2 lines. Electrons relaxing from the M shell produce Kv lines, while relaxation from M to L results in La lines, and so forth for higher shell. X-ray fluorescence spectrum. High-energy X-ray photons can interact with a sample causing the ejection of inner electrons. This interaction leads to the generation of an X-ray fluorescence emission spectrum. And then we have Auger effects. In addition to X-ray fluorescence, there is a competitive process known as the Auger effect, where an absorbed photon causes the internal conversion of energy, resulting in the emission of an electron rather than the emission of photon. Kay Mosley Law naman po, the research highlights Mosley Law, which correlates the reciprocal of the wavelength of characteristic X-ray series to the atomic number Z of an element, represented by the formula. Example calculation show that for the copper is Z is equal to 29 with a Ka1 line wavelengths of 0.154, and for nickel Z is equal to 28 with a wavelength of 0.166, consistent with the derived relationship. The research on the absorption of X-ray highlights several key findings. First is elemental filtering. Certain elements can act as the filters that selectively remove specific components of the X-ray spectrum, impacting the analysis and interpretation of X-ray data. Next is sample absorption. The absorption of X-ray is influenced by the thickness of the material being penetrated and is quantified by the mass absorption coefficient, which varies based on the atomic number of the element and the wavelength of the X-ray used. Next, nonlinear absorption behavior. X-ray absorption does not occur in a continuous manner. Instead, it displays distinct absorption edges. These edges are absorbed when the ionization energy for electrons in specific shells, like K, L, or M, is reached, leading to increased energy absorption for electron excitation. Next is the example naman po ng nickel. For nickel, the K-edge absorption occurs at 0.148, indicating that a nickel filter effectively absorbs X-rays from copper's Kv lines, which is 0.139, while minimally affecting the Ka line 0.154. This differential absorption is crucial for selecting appropriate filters in X-ray application. Next is complex matrices. In samples with complex compositions, all constituent elements contribute to the overall X-ray absorption, necessitating a comprehensive understanding of each element absorption characteristics. In X-ray emission spectrometry, there are two primary types of instrumentation. First is dispersive and non-dispersive, as illustrated in figures 2A and B. Here's an overview of how the dispersive instrument function, which is dispersive instrumentation. The X-ray source, the dispersive instrument utilizes a high-energy X-ray source, typically an X-ray tube that contains a target material like tungsten. Electrons are accelerated toward this target using a potential difference of about 50 excitation of the specimen. When these high-energy primary X-rays bombard the specimen, they induce the emission of characteristic X-rays from the elemental constituents of the sample. The emitted X-ray provide information about the elemental composition. And then, crystal analyzer. The emitted X-rays are then directed towards a crystal analyzer, which can be composed of materials like lithium, fluoride, or quartz. The purpose of this analyzer is to separate the emitted X-rays according to their wavelengths. And then we have a Bragg's law. The separation of X-ray is based on the principle of diffraction described by Bragg's law, which is mathematically represented as makikita po natin sa picture, where n is the order of the diffraction and the d is the lattice spacing of the crystal. And then we have analysis by varying the angle and measuring the intensity of the resulting diffracted X-rays. One can identify and quantify the different elements represented in the specimen based on their characteristic wavelengths. The research highlights efficacy of rotating a crystal to optimize the direction of successive X-ray beams onto a detector, such as Geiger-Müller tube, scintillation counter, or proportional counter. A significant finding is that the proportional counter's ability to generate signals proportional to the energy of incident X-ray photons can improve resolution and diminish background noise in X-ray detection. This method enhances the clarity of data collected, as illustrated in Figure 3, which shows the intensity of characteristic X-ray plotted against the angle. The finding emphasized the importance of detector choice and crystal orientation in maximizing the quality of X-ray diffraction data. In electron probe microanalysis, the specimen acts as the target for an electron beam, often produced by a scanning electron microscope or SEM, as depicted in Figure 2b. This technique allows for simultaneous surface imaging and elemental analysis, making it invaluable in material science and chemistry. A solid-state detector is employed to capture all emitted radiation at once. This capability facilitates the use of a multi-channel analyzer, which generates a series of voltage pulses that correspond to the X-ray spectrum emitted from the specimen. This method is commonly referred to as energy dispersive analysis of X-ray, or EDAX. The combination of imaging and elemental analysis enables researchers to examine both the morphology and composition of materials at a microscopic level, leading to a deeper understanding of material properties and behaviors. This dual approach is particularly beneficial in studying heterogeneous materials, as it provides insights into both the structure and chemical makeup of different pieces or components present in the sample. The detection and measurement of elements in a sample is crucial in various fields, including metallurgy, mineralogy, and petrochemistry. X-ray fluorescence, or XRF, is particularly beneficial as it allows for the analysis of complex solid samples without the need for labor-intensive wet chemical methods. An example is provided in Figure 3, which illustrates the analysis of a metallurgical sample containing silver, copper, nickel, and chromium. The advantage of XRF extend beyond metallurgy. It is advantageous in analyzing mineral and cement composition and examining petrochemical products. Electron probe analysis, coupled with energy dispersive analysis of X-ray EDAX, facilitates precise analysis of small areas, typically about 1 mm in diameter. This capability is especially useful for studying the distribution of additives in polymers and detecting high concentration of elements of interest in biological samples. Overall, the ability to conduct detailed elemental analysis with minimal sample preparation not only saves time but also enhances the accuracy and reliability of results, making these methods indispensable indispensable tools in both research and industrial application. I have example in X-ray emission spectrometry. Ito ay yung environmental monitoring. One engaging application of X-ray emission spectrometry that student can relate to is environmental monitoring. Consider a student project focused on studying the effects of heavy metal pollution in local areas, local water resources, or soil. The students can collect samples from different locations such as nearby rivers or industrial areas where contamination might occur. Once the samples are collected, the students can utilize XES or X-ray emission spectrometry to analyze the elemental composition of the samples. By exciting the samples with a focused X-ray beam, the student can generate a spectrum indicating the presence of various elements, particularly heavy metals like lead, arsenic, cadmium, and mercury, known to pose environmental and health risk. Step in the project po is yung sample collection. The students visit different sites and collect water or soil samples, ensuring to follow proper procedures for sample preservation. Next is preparation for analysis. Kukonduct po sila ng analysis. The samples may need to undergo certain preparatory steps such as drying or grinding to ensure they are suitable for X-ray emission spectrometry analysis. And then next is conducting X-ray emission spectrometry. Utilizing a laboratory equipped with X-ray spectrometry tools, the students can expose the sample to X-rays. Specialized software will analyze the emitted X-ray spectrum. Identify the elements based on their unique energy signatures. Next is data interpretation. The students will interpret the resulting data, comparing the concentration levels of heavy metals against regulatory standards to assess the safety and quality of the environment. Next is communication of results. Finally, the students can compile their findings into a report or presentation showcasing the significance of their research and advocating for environmental protection if contamination is found.